Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries along with the SDL2 library so we can display results in a window. This, of course, using SDL2 library means we should be fairly cross-platform compatible, so although I'm coding in Linux, it should be possible to follow along in Windows as well, or whatever other operating system you care to use. Okay, so the episode today we're going to focus on procedural textures, and this is going to be the first of a two-part look at procedural textures, because when I really came to look at it, there's quite a lot to go over, and there's lots of interesting things we can talk about to do with Perlin noise and that. And we're going to come to that in the second episode. What I really wanted to focus on today was simply getting the basics out of the way so that we've got the code base ready to really start exploring that properly. So anyway, I don't want to talk for too long. I really hope that will be of interest. If you like this video, please do remember to hit that like button. It really does help with the YouTube algorithm. And if you haven't subscribed already, then please consider doing so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's have a look at procedural textures. So here we are, this is episode 14, part 1, as I've just said, of our look at procedural textures. And I wanted to start just by having a quick recap of UV space and basic texture mapping principles, which we have talked about before. So the UV space is basically a two-dimensional space that we define over the surface of any three-dimensional object. And we orientate our space, U, we consider here arbitrarily to be the horizontal axis and V the vertical axis, and we consider the space to exist between U and V both from -1 to +1, with 0, 0 obviously being in the centre. And that gives us then a perfectly square space, and then we can stretch and distort and map that in any way we wish onto the surface of our 3D object. So, as an example, if we consider a sphere, and if you go back and look at the episode I did on texture mapping, there's a lot more detail on this. But if we consider the example of a sphere, although a sphere is a three-dimensional shape, its surface is only two-dimensional. And any point on the sphere can actually be expressed in spherical coordinates, given by U, V, and R, where R is the radius of the sphere, so that's a fixed quantity for a particular sphere. And then U and V simply describe the angles around these circles. So in this case, U would be the angle around the orange circle, and V the angle around the yellow circle. Okay, and you can see then that assuming that R is fixed, which in our examples it always will be fixed to 1, you can see that the two coordinates U and V are enough to describe the position of any point on the surface of our sphere. And then we simply have to find a mathematical way to map from our position in three-dimensional space into a two-dimensional UV coordinates. So, what are procedural textures? Well, we can actually map any 2D data, such as an image, to our UV space, and indeed we have already looked at that. I did an episode a few episodes ago where we looked at image textures. And often that's exactly what we'll do. We'll take a picture of some sort and then map that onto the object's UV space in order to give that object some kind of realistic texture. And that picture could be of any form. It could be a wood pattern, or it could be something to represent grass or brick pattern for a wall or something like that. But there are disadvantages to doing textures that way. I mean, in principle, you could do any texture like that. But the disadvantages are the image is fixed. Okay, so difficult to vary it. The resolution is fixed, so it might get blurry if you get very close to the object. Now, there are ways around that. You can have multiple resolution versions of your image and switch between them depending on the position, but then that brings in its own issues as well. And also, you have to include all of the image data along with the rest of the scene, which, can get cumbersome and difficult, and there might be cases where you don't want to do that. So a procedural texture, on the other hand, is actually just a mathematical description of the pattern that we want. And we've actually implemented a very simple example of this already in the form of the checker pattern. And again, in a previous episode, in the episode on texture mapping, we showed how to implement a basic texture pattern, and we produced this image here where more or less every object apart from this one, has been mapped with the checker pattern. And you can see how the three-dimensional surface is converted into the two-dimensional UV coordinates, and you can see how the texture has been mapped onto those objects. Okay, so the code to implement the checker pattern is actually really very simple. We're going to look at the code in more detail in a moment. We have a simple function within our texture class, our checker class for the texture called getColor, that accepts as input a two-dimensional vector with the UV coordinates. We apply a local transform to it. Again, I'm not going to go over that in great detail now. That was described before in the previous episode. We get new U and new V. And then to implement the actual checker pattern, all we have to do is we create an integer variable called check that is simply equal to the sum of the floored values of U and new V. And they're all static cast to integers. And then we simply do a check. If check modulo 2 is equal to 0, then we have color 1, else we have color 2. And that is actually all that we need to do to implement the very basic checkered floor pattern. Okay, so a procedural texture is simply some code that defines how we map the values of U and V to some particular color. Once we have the UV coordinates on the object surface, we then use these to compute the color of the texture at that point. Now we can write all sorts of code to create very complex patterns like wood and marble, clouds, whatever we might want. For this episode though, we're going to focus on the very simple example, the gradient texture. Okay, so but before we can talk about gradient textures though, we need to talk about a color map or color maps. A color map simply defines how a scalar value between 0 and 1 maps to a color. So for example, we might have this gradient here from black through to red, and we see we have the value here of 0, a half, and 1. So this is a position in our color map, the value. Okay, so when the value is 0, our corresponding color is black. So that's 0, 0, 0 in RGB. When our position or value is a half, we have a color of 0.500, so that's RGB, so 0.5 for red, 50% red. And then when our value is 1, we have 100 for RGB, or 100% red, and that would describe that gradient. Okay. So we can actually define a color map using a number of stops, which define the color at a particular value. So for example, in this case now going from yellow through to red, we have two stops, stop 1 at value 0 and stop 2 at value 1. And in this case, the color at stop 1 is yellow, which is 110 in RGB, and at stop 2 is red, 100. And anywhere in between is then simply the linear interpolation between those two colors. If we represent each color as a four-dimensional vector, because we're including an alpha channel, so it's RGBA, red, green, blue, alpha, okay, then we have something like this. So we have the stop at the first stop is given by x1, which is the value, and then the vector y1. Okay, so x1 vector y1, so we have value of 0, this is for the gradient that we just saw, so at the value of 0 we have y1, which represents our colour as 1101, so that's 1 for red, 1 for green, 0 for blue and 1 for alpha, which is of course yellow. And our second stop we have x2 vector y2, so x2 is 1, and our vector y2 is then 1001, which is 1 for red, 0 for green, 0 for blue and 1 for alpha. And then actually it's really simple to compute the color at any value of x using simply this. So the vector y of x is equal to y1, that's this one here, the vector y1 plus simply x minus x1, okay, multiplied by y2 minus y1 divided by x2 minus x1. And that is very simply the formula for linear interpolation, nothing fancy going on, except that we're using vectors, but representing it this way is just quite straightforward because it means we deal with all the RGB and A values all in one go. So that's it. That's pretty much all that we need to implement in order to do color maps. But we can have more than just two stops. I mean, if we limited ourselves to just two stops, that could get pretty boring. So in this example, we go from yellow to green and then from green to blue. So we have three stops. Stop 1 at value 0 is yellow, stop 2 at value 1/2 is green, and stop 3 at value 1 is blue. And in this case, we simply determine which two stops our value of x is between and then perform the linear interpolation between those. So in this case, if x is between 0 and 1/2, then we have that x1 is 0 and y1 is equal to 1101. Okay, so that's yellow. And x2 is 1/2 in this case, and y2 is 0101, which is of course green. If x lies between 1/2 and 1, then we have that x1 is 1/2, and y1 is equal to 0101, which is green, the same there, and x2 is equal to 1, y2 is 0011, which is, of course, blue. And we can do that for as many stops between 0 and 1 as we need. Okay, so to create a gradient texture, all we need to do is to map our values of UV to a scalar value between 0 and 1, and then use our colour map to compute what colour that should be. And we're going to see an example of that when we come to look at the code. Okay, so that's really it for the theory that I wanted to cover. There's not too much there, but I think it's important to get this out of the way before we sort of move on to looking at more complicated things to do with procedural textures. So let's jump in and let's have a look at how we can actually implement the color map class and the gradient texture class in our code, and how we can create an interesting scene to show that it does indeed all work. And also we're going to cover a couple of extra things. I also want to look at texture stacking, which is a feature that we did build into the code originally, but then didn't explore any further, and also blending of colors with alpha maps. But we'll see that in a moment. So let's jump in now and let's have a look at the code. Okay, so just before we start exploring the code, I'm here just at the terminal, and I just want to show this is the code that we have. If you clone the repository from GitHub or download it from there, or if you've been following along, you should have something similar to this. If we go into the actual QB raytrace folder, we can see we've got all our code here. We're primarily going to be looking at the QB textures and QB materials subdirectories today. So let's just go into QB textures, and what I've done is I've created some new files here. We've created colormap.hpp and colormap.cpp for our colormap class, and then I've created gradient.hpp and gradient.cpp for our gradient texture class. I've also made some minor changes to some other files there, but we'll talk about that in a moment. And also in the QB materials subdirectory, made some minor changes to simple material and to material base, but we'll see about that in just a moment. Okay, so this is the color map header file for the color map class, so colormap.hpp. We have our include guards, as we always do, and we hash include qbvector.h from the linear algebra library, qblinalg, which should be included with the code. And we're putting everything into our qbrt namespace and then into our texture sub namespace, and of course we're defining our class as color map. As usual, we have our public constructor and destructor functions. We're not inheriting from anything for this, so it's pretty straightforward. We have a function to set a stop as a color, so void set stop. It accepts a double input for the position between 0 and 1, and a QB vector input for the actual value. So that would be a 4-dimensional vector there. And of course we have a function to return the color at a particular position, which is qbvector double get color double position. So it accepts as input a double representing the position between 0 and 1, and it returns an instance of the qbvector class of type double, like so, as you'd expect. And we have a couple of private variables. We have a vector an std vector to store our stop positions, and an std vector of qb vectors of type double to store the actual stop values. And that is it. That is all the code that we need for colormap.hpp. Let's have a look at colormap.cpp. Okay, so this is the colormap.cpp file. It's pretty straightforward. We just hash include colormap.hpp, obviously. We have our constructor and destructor functions. We don't need any code in those at all. And we have our code to set a stop, so set stop, which accepts as input a double representing the position and a QB vector object of type double representing the value. And we simply do m underscore stop positions dot pushback position and m stop values dot pushback value. That's really straightforward. It's just going to push those back into the std vector variables that we created in the header file. Okay, so the interesting stuff that goes on actually happens, of course, in the getColor function, which accepts as input a double representing the position. So the first thing that we have to do, as I mentioned when we were looking at the slides just now, is we find the two stops that are closest to the current position. Okay, so we set num stops is equal to the size of the m underscore stop positions variable. Pretty straightforward. We set first stop and second stop, both of those declared as integers. We set them initially to 0, and we define our diff initially as being 2. So that's going to measure the difference between where we are and where we want to be. So that's double diff equals 2. And we then simply loop through all of the stops using for int I equals 0, I less than num stops plus plus I. Okay? So we define a variable t, double t is equal to the current position, so m underscore stop positions at I minus the position that we are interested in. Okay? And if the floating point absolute value of t is less than diff, then we set diff equal to the abs value of t. We set the first stop therefore equal to I, okay? And if t is less than 0, then we set the second stop being to the minimum value of num stops, or I plus 1, Else, if t is greater than 0, then we set second stop to being the maximum value of I minus 1 or 0. And if t is 0, then second stop simply equals I, because that means we're exactly on a stop. If you think about that, maybe put it down on a piece of paper, you'll see what's going on. We're simply deciding which pair of stops should be the first and the second based on where we are specified by position. Okay, so if the position was exactly at a stop, then we simply return that value. So if first stop equals second stop, return m underscore stop values at first stop. Okay, that's really straightforward. Otherwise, we actually need to do a linear interpolation between the first and second stops. So first of all, we make sure that the stops are in the right order. So if second stop is less than first stop, then we use STD swap, first stop, second swap, simply to swap those around. And what that means is simply that the first stop always comes before the second stop. That just makes the linear interpolation easier. We are then going to perform the linear interpolation simply using an implementation of y0 plus x minus x0 times y minus y0 divided by x1 minus x0. Okay? We define double x is equal to position, not really necessary, but just makes it easier. x0 is m underscore stop positions at first stop, and x1 is m underscore stop positions at second stop. And we return m underscore stop values at first stop plus x minus x0 multiplied by the stop value at the second stop minus the stop value at the first stop, all multiplied by 1 over x1 minus x0. Now we have to do it this way, multiplied by 1 over x1 minus x0, because the current implementation of the QB vector class doesn't allow for dividing two vectors. It only allows you to multiply a vector by a scalar. It doesn't allow you to divide a vector by a scalar, sorry. So we multiply by 1 over x1 minus x0, which of course is the same as dividing by x1 minus x0. Okay, and that's everything that we need to implement a basic colour map. Really actually quite straightforward. The only slight complication is here, where we have to decide exactly which two stops lie either side of our current position. But I think if you work that through, you'll not have any difficulty understanding that. Okay, so the next thing then to talk about is how we could actually use that colour map class to create a simple gradient texture. So we're going to look here. This is gradient.hpp, the header file for the gradient texture class. For this, we are going to inherit from texture base. So we need to hash include texturebase.hpp, and we hash include colormap.hpp, because of course we need that. We're operating in our QB-RT namespace and then in the texture sub namespace, and we define our class gradient, which inherits from public texture base. Okay, we have our constructor and destructor, which are the same as before, except we have a virtual destructor now, which we have to override. And then we have a function to return the color, so virtual QB vector double get color, so which accepts as input a QB vector object with the UV coordinates in it, and we override that from the base class. And we have a function to set the stops for the color map, void set stop, accept as input a double for the position and a QB vector object for the value. And we have a simple private variable, just one, that it stores an instance of the color map class called m underscore color map. And that is it for the gradient.hpp file. Let's have a look at gradient.cpp. Okay, so this is gradient.cpp. It actually is. I'll just fix that, there we go. This is gradient.cpp. We hash include gradient.hpp, of course. We have our constructor and destructor. We don't have any code in those. You'll notice this is a very short function, so this is the whole code here. And our function to return the color simply accepts as input the UV coordinates, okay, and it's going to return a QB vector object of type double. We apply the local transform to the UV coordinates. This is common to all of the textures in the system that I've implemented. We did talk about that in the episode on texture mapping, so go back and have a look at that if you want to. Once we've done that, we get our new lock, which is a QB vector object containing our new UV position. We extract new U, simply being the minimum of new lock.getElement 1 plus 1 divided by 2, comma 1. And all that's going to do is actually scale our value so that it runs between 0 and 1. Okay, so as I mentioned at the beginning, our U and V coordinates run from -1 to +1. But our color map class works on values between 0 and 1. So we take our value of U, we add 1 to it, so we then get a value that goes between 0 and 2. We divide that by 2, which gives a value between 0 and 1. And we don't want it to be able to go over 1, so we use std min. So we're going to return either this value or 1, depending which is smallest. And all we actually do is simply then return m_colorMap.getColor new u. So that is using the getColor function from the colorMap class that we just talked about, simply passing the new u value, which is this scalar quantity here, and then that returns the color that we need. And then the only other thing that we need to do is a function to set the stops for the colorMap. It accepts as input a double for the position and a QB vector object for the value, and it simply passes those straight to the colorMap instance, m_colorMap.setStop, position and value. And that is all of the code that we need to implement a basic gradient texture. Okay, so that's colorMap and gradient texture implemented. Now, before we can actually use those, we do need to make some other minor changes to the code. And also, as I mentioned, I wanted to implement code so that we can do texture stacking. So that means that we can define a texture with an alpha value, so it's transparent or semi-transparent in at least some areas, or maybe over the whole thing, and we can have another texture then behind that, so that we can have, in principle, as many textures stacked together as we like, and we can use that to create some quite interesting effects. And I'm also going to modify the original implementation of the checkerboard texture so that we can actually assign a different texture to each of the checks rather than just a color. So rather than just two colors, we could actually have complete textures there. So let's have a look. Let's jump in and have a look at how we can do that. Okay, so to start with, I'm going to look at the checker class. This is checker.hpp, the header file for this, the code that we created. I think it was back in episode 9. There's a link in the description below, of course, to that. So I'm not going to talk about this too much because we covered it before. The only thing that has changed since the last version now is in the private section, we are now declaring that we have these as previously these were QB vectors, so we stored them as colors, but now we're having std shared pointer to qbrt::texture::texture base. So we define these two colors for our checkerboard now as instances of the texture base class. Okay, now if you recall back to the episode on texture mapping, we did make the effort to make a flat texture, and that probably did seem rather pointless at the time, but the reason I did that is thinking ahead to doing this. What that means, if we do just want a plain color, we can simply use the flat texture. Okay, so we don't lose any generality by doing things this way. Okay, let's have a look at the CPP code and look what's actually changed. So checker.cpp, we don't need to bring in a lot here. We do need to hash include flat.hpp here, as well as checker.hpp. Okay. We probably don't need // there because it's coming from the same folder, but never mind. Anyway, so some minor differences here. When we call our constructor for this, we initialize with default values. Okay, so we set color1. So what we do is we create two instances of the flat texture called color1 and color2. And we then set their colors using the set color property for those two. And then we're going to store those as m_p color1 and m_p color2. We're going to store those using this syntax here. So we create a shared pointer of type qbrt::texture: flat of color1 and another one to color2. Okay, and that will set us up with the default, and we see these are going to set up as white and dark gray. Okay. Our destructor, as before, has no code. Our function to return the color is very similar. So we see this really hasn't changed at all. All we do is you call for local color simply m_p_color1 get color UV coords, or m_p_color2 get color UV coords. Okay, that's the only change there. And a minor change here with set color, because we're now accepting as inputs differently. We now indeed have two set color methods. So we have set color here, which accepts as inputs two shared PTRs, two shared pointers to input color 1 and input color 2, both of type texture base, and then we simply do the assignment like that, very straightforward. And if the user passes two constant colors, we maintain compatibility. It's the simplest way of using the class. I didn't want to, if I wanted to create a simple black and white checkerboard, have to create two flat textures myself to do that. So we can actually call set color and pass to it simply two QB vector objects representing the colors, and then simply as we did in the constructor, we create the color 1 and color 2 instances of the flat texture, set their colors, and then simply assign those like so. Okay, and that is everything that we need to modify in the checkerboard texture to allow us to either have fixed colors for each check or indeed another texture. And this is something that we're going to see as we implement more complex textures as well. I want to try and have that option to, rather than just having fixed colors, you can actually have a different texture within part of another texture. That creates a great deal of flexibility and allows us to do some really interesting things, as we'll see in subsequent episodes. Okay, so the other thing that I had to change, made some minor changes to the material base class. Okay, so this is in the QB materials subfolder, and the slight difference that we have here, yes, here we go. Yes, so the only difference is I've done here, we set this up originally to allow texture stacking, to allow the use of multiple textures, but then we fixed it to always just use the first one in the list. So we right from the start, we set this as being an STD vector object to store all our textures, but we then fixed our code so that we would only ever consider the first one, and that's what we're going to change today. So we've added two functions here. We've added a function here to return the color due to the textures at a given UV coordinate. We'll see why in a moment. Okay, so that simply get texture color returns a QB vector type double, accepts as input, of course, a QB vector type double for the UV coordinates. And we have a function to blend RGBA colors, which blends into color one. Note the return type of this is void, and it will blend into this. So this one is not declared const color one, and we have const color two. So we blend color two into color one. Okay, that is everything that we've changed in materialbase.hpp. So let's have a look at materialbase.cpp. Okay, so here we are, materialbase.cpp. We don't have to change very much here. Simply some minor changes in where yes, here we go, simply implement these two functions. So first of all, we have materialbase get texture color. Okay, this defines initially an output color, 4-dimensional vector for the output color. If our texture list size is less than 1, then we simply set m_texturelist.at0.getColor UV coords, and that's our output color, really straightforward. If, on the other hand, we have more than one texture assigned, so we want to do texture stacking, then the output color is going to start as being the color due to the first texture. Okay, so we assume that the 0th texture is the texture right at the back of the stack, right at the bottom of the stack, if you like, and then we're going to loop through all of our different textures, so m_texturelist.size, and we call the blend colors function, and we blend into output color, and we mTextureList_.i.getColor. So we're going to get the color at this UV coordinate for every texture and blend it into output color, and we do that through a loop. So at the end, output color will contain our final blended color, which we then simply return. So that's pretty straightforward. The real work is done here in the blend colors function, which accepts as input our two colors, remembering that we are writing into color one, so it's not const. And this is very simple, very simply a linear interpolation based on the alpha values. Okay, so color 1 is simply equal to color 2 multiplied by color 2.getElement3, okay, plus color 1 multiplied by 1 minus color 2.getElement3. Okay, really straightforward. And that is simply going to do a linear interpolation between those two colors based on their alpha values. It's a very simple implementation of alpha blending. There are other ways of doing alpha blending. It is worth noting. This, to my mind, in my way of thinking about it anyway, is the simplest way of doing it. And I hold my hand up and say, you know, that this may not be necessarily the best way of doing things, but that's something we can explore later in other episodes and things. It does, at least in my testing, appear to work as it should. So there we go. Disclaimer there. Okay, and that is everything that we've done in material base. Okay, so the last thing that we need to talk about is changes that we've made to the simple material class. This is our really basic material class that we're using for pretty much everything. It's simply called simple material. It can have now any number of textures assigned to it or color, and it handles the reflectivity, shininess, and all of that sort of thing. Okay, so what we've changed here is actually very simple. The only difference is here. So if we have a texture, so here we compute the diffuse color component, and that's what we're going to use for the texture. So if we don't have a texture, we simply return mbase color. And now, if we do have a texture, then we call the getTextureColor function, and we pass to it the UV coordinates extracted from the current object. Okay, so that hasn't changed a lot. If you go back to the episode on simple materials, you see how this basically works. But now, instead of simply before, what we did was simply we got the texture from the first texture assigned to this particular material, and now we call the getTextureColor function, which, as we've just seen, will then go on to implement the alpha blending to combine all of our textures together if we have indeed more than one. And that is the only change actually that we've made there. The rest of that code remains as it is. Okay, so that is basically everything. It's a slightly shorter episode today because, we just wanted to get this basic stuff out of the way. The final thing to look at, let's just quickly look at the scene class, so how we can create an interesting demonstration of our new texture capabilities. Okay, so this is scene.cpp, our class that creates the scene. So we haven't changed anything really much here with the camera and everything. Ambient lighting is all as it was. What we do have that's different is we create some textures. We create our floor texture. Okay, this is an instance of checker. And we're going to set this up using two plain colors. As we've just seen, we can still do that because we overloaded the set color function of the checker class so that we can pass two QB vector objects, and then it will create the flat textures for us. We define our gradient texture, so this is for testing that we can actually do gradients. This is an instance of the gradient class. We set the transform. We have to do that in every case. Okay, so just to recap, this is the translation, rotation, and scaling for our textures. Okay, so for the floor texture, we scale that up to 16 by 16. For the gradient texture, we're going to leave that at 1 by 1. We then set 3 stops. We set stop 1 to red, we set stop 2 at a half to green, and stop 3 at 1 to blue. So we go from red to green to blue between 0, a half, and 1. Okay, we're going to define 2 checkerboard patterns called small checks 1 and small checks 2, okay, instances of checker, and these are flat textures just made with plain colors. So small checks 1 we set to be checks with white to a bluish color. Okay, that's going to be a nice blue color. And small checks 2 we set to be black to red, green, blue, a kind of yellow color. Okay. Right. And then we're going to create our layered checks texture, and this is a demonstration of how we can now do texture stacking. This is a basic implementation of the checker class, okay? And now set color, instead of passing 2 QB vector objects representing colors, we now pass small checks 1 and small checks 2. So we're passing 2 textures into our layered textures class. So that will then create a checkerboard pattern made out of those 2 textures, and we'll see what that looks like in a moment. And we then also create an alpha gradient to demonstrate alpha blending, which is rotated a little bit, m pi by 4, to rotate by 45 degrees. And we set 3 stops here, 0, a half, and 1, which we set those to, that is to blue, to yellow, to red. Blue to yellow. And we set our alpha values 1, 0, and 1. So that will go from blue, so full blue to then full white, right, so we're going from blue to white to yellow, but when we get to stop 2 at a half, alpha value is 0, so there'll be nothing there, and then we go back to an alpha value of 1 when we get to yellow. Okay, and then we create some materials. We create a floor material, which we assign the floor texture. We create an image material to which we assign the gradient texture, and then we create a layered material to which we now assign 2 textures, being layered checks and alpha gradient. Okay, so layered checks is the bottommost layer, and alpha gradient will then be on top of that. And then we create our objects. We create our image sphere and assign the material image material, and we create an image plane and we assign the layered material, and we create an image box and we assign image material, so that have the same material as the sphere. And then our floor, we simply assign the floor material. And we push those into the scene, and we've talked about everything else that we have there in the scene class before. Okay, so that's it for the code. Let's look at the terminal. Let's jump to the terminal, let's compile that, and let's show that it works. Okay, so it's going to run make clean, tidy that up first. So let's run make, compile everything. Our code base is getting fairly large now, so we do have quite a lot now to compile. It does take a few seconds to run through. Okay, there we go, and let's just run /QBRay and show that that does indeed work. It's a fairly simple scene, so it renders quite quickly. But there we go, that is our very basic demonstration. We see that we have the cube and the sphere with the gradient texture, and we have our layered texture going on here. So we have our checkered pattern where each check is now a separate checkered pattern, so that we can combine textures together, and then we've layered that with the alpha gradient texture over the top. So that is really everything that I wanted to talk about today. Now, The second part in this two-parter series is going to be a lot more interesting. I want to go on to look at Perlin noise and how we can use that to create some really interesting effects, marble patterns, wood patterns, that kind of thing. But I felt if I did all that together with what we've talked about today, that would have just been far too much. So I think it was worth getting over this basic theory, making the minor modifications that we've needed to make to the code base to make all of this work. And now we're in a very good position to go forward and look at much more interesting things in the next episode. So anyway, there we go. As I said, that's everything I want to talk about today. If you've enjoyed this video, please do remember to hit that like button. It really does help with the YouTube algorithm. Thank you very much. Well, yeah, I mean, I really hope you've enjoyed it. It's been a great deal of pleasure making it, as it always is. And yes, so anyway, I will really look forward to seeing you in the next episode. Thank you very much for watching. Bye.